I know you guys were missing the video intro. You guys have probably were disappointed that you haven't seen that yet in this series of videos, so I didn't want to let you down. By the way, if you couldn't quite put your finger on it, you were like, something about Mr. Jamie reminds me of Tom Cruise. It is that in that video, just like Tom Cruise, I did all my own stunts, right? So there is no stunt double used in any of that stuff. That actually was Mr. Walker's face that the Diet Coke was hitting in that one scene. So just wanted to make sure you guys were aware of that. All right. Let's talk about something today called Gibbs free energy. All right. Before we discuss what that is, let's remind ourselves that we said whenever you're discussing entropy, you not only consider the entropy of the chemical reaction, but you also have to consider the effect, how the entropy is affected on the surroundings of the chemical reaction. And so really to look at the entropy as a whole, you have to take both of those into account, the entropy of the reaction and the entropy of the surroundings. Well, we haven't learned a way specifically to calculate the entropy of the surroundings yet, but we actually kind of have, and that is when we considered the topic of enthalpy. What is enthalpy? Enthalpy has to do, change in H, has to do with that's where we determine whether a reaction was exothermic or endothermic. If it was exothermic, it was releasing energy into its surroundings. If it was endothermic, it was absorbing energy from the surroundings. And so as it turns out, change in H is actually an expression of how the reaction is affecting its surroundings, right? How entropy is affected by the chemical reaction. And so knowing change in H and then also change in S, now that we've learned how to calculate that for a chemical reaction, we can actually kind of get a pretty good picture of what's going on overall when we consider the entropy of a particular system. And so that's what Gibbs free energy is all about. It's a way to put those two together. And this Gibbs free energy value, noted by the change in Gibbs free energy, change in G, capital G, is equal to the change in H, the change in enthalpy of the reaction, minus the temperature times the change in entropy for the reaction. And one thing to note, because of the units of change in S, we got to make sure that our temperature is in Kelvin. If it's not, we need to convert it to that before we can use this equation, okay? And the important thing to take away from this equation is that if a reaction, if it has a change in G that's less than 0, so it's a negative number, then the reaction is considered to be spontaneous. Now, what do we mean by that? It means that, that the reaction will actually continue once it gets started. It doesn't mean that it'll just all of a sudden start on its own. Remember, we discussed activation energy, and you've got to have the correct amount of activation energy for a chemical reaction to start. But once it gets started, it will continue without any outside intervention if it is a spontaneous reaction, right? So if it's greater than 0, it will not be spontaneous. If it's less than 0, it will be. And so just a couple of quick things to note here. Notice that if change in H is a negative number and change in S is a negative number, change in S is a positive number, then you've got a negative number minus a positive number, and the result then will have to be a negative number, right? So if you've got a negative for this change in H and a positive for change in S, then the reaction will always be spontaneous, right? Overall value will be less than 0. The opposite is also true. If this is a positive number and this is a negative number, then a positive number minus a negative number is always going to be a positive number. So if these values line up like that, then the reaction will not be spontaneous, okay? But and the reason I say that is because remember, with some of these reactions, like when we were figuring out change in S, we could determine the sign very easily without having to do any calculations. So it could be that you could just observe the reaction and say, oh yeah, it's spontaneous or it's not, if one happens to be negative and the other one happens to be positive. But for every other case, you're going to have to actually use this equation to calculate it, okay? So let's do an example of that. And the example says, determine whether or not the following reaction is spontaneous at 25 degrees Celsius. Okay, so carbon dioxide in gas form plus hydrogen in gas form yields carbon monoxide in gas form and water in gas form. And so is the reaction spontaneous? In other words, is change in G less than 0 for this particular reaction? Well, believe it or not, we have all the information that we need in order to do this, this particular problem here, to calculate this. But we're going to have to figure out what change in H is, and we're going to have to figure out what change in T is. I'm sorry, not change in T, change in S is. We've been given T. And so what we're going to have to do is use our tables. One table is on page 424, the standard enthalpies of formation. And so if we look that up, we can calculate the change in H for this reaction. And we'll see that the change in H is going to be, we have 1 mole of CO on that side, 1 mole of CO. And the standard enthalpy of formation for that particular substance in gas form is going to be negative 110.5 kilojoules per mole. All right, and so for the sake of space, I'm not going to write down the units for the rest of them, but we just want to make sure that our units are canceling out, right? Moles are going to cancel out here, and you're going to be left with kilojoules for the value. So plus 1 mole times the enthalpy for H2O in gas form, and that's going to be negative 241.8, minus the enthalpy for CO2, the enthalpy of formation for CO2 times 1 mole of that. So we've got negative 39393.5, and then minus for H2, we remember that it's going to be 1 mole times 0. So because the standard enthalpy of formation of an element in its natural phase is always 0, right? So if we punch this in our calculator, we get a change in H equal to 41.2 kilojoules. And so just because our next value is going to be in joules and not kilojoules, I'm going to go ahead and write that as joules. So that is going to be 41,200 joules, okay? Now change in S. Change in S, now we're going to use the table that's on page 437, the absolute entropies table, to look up each of these values. And so we have the 1 mole of CO, and it has an absolute entropy of 197.5. And that unit is joules per moles K. Right, I told you it's in Kelvin, so that's why we have to convert our temperature to Kelvin. Times, again, I'm going to drop the units because of space. 188.7, that's the value for H2O, minus 1 times 213.7, that's the value of CO2. And then finally, remember with the in this particular table, the absolute entropies value, the element is not going to have a value of 0. It actually has a non-zero numeric value. It's going to be 130.6. All right, so we type all that in our calculator and we get a value of 41.9 joules per K. Okay? So the only other thing we need to do before we can enter all this into our equation for Gibbs free energy, which was change in G is equal to change in H minus T times change in S, is that we said T has to be in Kelvin, right? So they gave it to us in 25 degrees Celsius. So if we remember, T equals 373.15 plus, if we're converting to Kelvin, 373.15 plus the value that it was in Celsius, right? And so we get a final value rounded to 398 Kelvin. So let's plug that in. So change in G is equal to change in H, 41,200 joules minus 398 K times 41.9 joules per K. And we get a final value of 28. Wait a minute, something's not right here. What did I do wrong? Oh yeah, that's right. That's what's wrong. 298. 298 right there. So I said I did this wrong. This should be 273. My bad. 273, 298. So we get a final value of 28,700 joules. All right. So that's the change in G. And so the original question, though, was, is the reaction spontaneous or not? And because this is greater than 0, it's not less than 0, then the reaction is not spontaneous, right? Okay, so the other cool thing that we can do is not only can we figure out whether or not the reaction is spontaneous, but if we know what change in HR and what change in S are, if we know what change in H is and what change in S is, we can also figure out what temperature range this reaction what the temperature range would be for this reaction to be spontaneous. And that's what the next example is asking us. So example 14.8, and this problem says for the same reaction that we just calculated change in H and change in S for what temperatures is the reaction spontaneous, right? So we're trying to figure out if it wasn't spontaneous with the temperature that it was at, 25 degrees Celsius, what temperature do we need in order for it to be spontaneous, right? And so how do we figure that out? Well, we know that it's spontaneous when change in G is less than 0, right? So this entire side of the equation here has got to be less than 0 if it's going to be spontaneous. So let's write that down. Change in H minus T times change in S has got to be less than 0 for it to be spontaneous, right? So let's plug in our values here. We'll write this as joules again like we did last time. 41,200 joules minus some value of T times 41.9 joules per K has got to be less than 0. All right? So what we want to do is we're going to move this over to the other side of the inequality first. So T times 41.9 has got to be less than negative 41,200. And then to, there's a negative sign here, sorry. And so to get T on one side all by itself, we're going to divide both sides by negative 41.9. Okay? Negative 41.9. Now when we do that, one thing you have to remember with inequalities is when you divide or multiply both sides by a negative number, then you've got to flip the inequality, right? So we're going to have to change this from a less than to a greater than when we do this division by a negative number. So T then has to be greater than, and when we plug this value here, sorry, that should be a negative 41.9 there. When we plug that into our calculator, we get a value of 983 K. And so the final answer is that this reaction will be spontaneous if the temperature is greater than 983 K. All right? Okay, one more quick thing that I want to go over with Gibbs free energy, and it's going to look extremely familiar because it's what we've already done both with entropy and enthalpy. Remember with enthalpy, we said that change in H was a state function. And so what that was why we could use the table of the standard enthalpies of formation, because we could look at those values, and so based on the substances that were in the equation, we could use those figures in the table to calculate the overall change in enthalpy. We can do the same thing with change in G if we have a table of standard Gibbs free energy of energies of formation values, and we have such a table on page 444. All right, and so just notice with this table here, just like when we had the standard enthalpies of formation, it's written as, it's got this little, when it says change in G, it has the little degree symbol there, and it has a little F down there. That means change in G of formation. The degree symbol means it's at 25 degrees Celsius, right? So these values are only good at room temperature, all right? And so the equation for calculating this is going to look very similar to what we had for change in H, but the one thing that we need to note with this also is that this value is only, like I said, is valid at 25 degrees Celsius. And the other thing is that this and it's 0 for an element in its natural phase. Right, so we saw that to be the case with the change in enthalpy of formation as well. All right, so given that, if we have an equation that is, an equation that looks like this: A, little a, big A. So moles is little a, big A here, plus little b, big B, and it yields C, capital C, plus D, capital D. Then we can say that change in G, make sure you know this, right? Make sure you know this. Change in G is going to be equal to C, change in G, F degree. This is really getting cumbersome. Let's instead of doing the time travel thing, let's do the blur transition. All right. So as I'm talking, we're just going to kind of blur, and all of a sudden you're going to just see that the equation is there. Okay. And so we're going to start working with. So having written this all out here, we can see that similar to what we had with change in H, that this would be the equation for it. And it's basically, you could write it simply as the sum of the change in G of formation of the products minus the sum of the change in G of formation for the reactants, okay? So let's just plug that in. That's going to be simple to do. We've got one problem here where we can use that, and I'll leave that one equation down at the bottom there. And it says, is the following reaction spontaneous at 25 degrees Celsius? And they give us C6H6 plus 12 H2O in liquid form. Notice that the phase of the substance matters. 6 moles of carbon dioxide in gas form plus 15 moles of H2 in gas form. Okay? And so all we're doing is we're just looking this up on the table and we're plugging in these values, right? So we first do it for 6 CO2. So we've got 6 moles of CO2. We see that it has a value of negative 394.4 kilojoules per mole. And again, I'm going to leave the units out for space. We've got 15, this is hydrogen in its natural phase, and so it's going to have a value of 0, right? Minus 1 mole of C6H6, so that has a value of 124.4 based on what the table tells us. And then finally 12 moles, minus 12 moles of negative 237.1 kilojoules per mole, and that's the value for H2O in liquid form. So we calculate change in G then to be 354.4 kilojoules. And just like we saw with our last reaction, this reaction at 25 degrees Celsius is not spontaneous, right? Not spontaneous. Don't forget to write that down if that's what the question is asking you, right? It's not spontaneous because change in G is not less than 0. So that's it for today. You guys let me know if you have any questions, and I will see you next time.